Hi, everyone. Welcome to the lecture video for section 2.3. This is the second time I'm recording this because I incorrectly shared my screen last time. So I'm not going to write everything again and my hand will cramp, but I'll talk through it. So this section 2.3 is all about slope. Slope is a rate of change. And we usually think of it as the rate of change in y divided by the change in x. Y and X are usually the variables we use. Y is output and X is input. So the slope is the change in the output divided by the change in the input. And I want to point out that slope, as a mathematical idea, only applies to linear functions, equations, or models. So it's only functions or equations that describe lines. If the graph is not a line, then the graph does not have slope. And in this video, I'm going to talk through our four representations of mathematical ideas and talk about slope in each of those four. So let's start with symbolic. I've already shown you a couple times that y equals mx plus b is our slope-intercept form. And from slope-intercept form, the m is the number that tells you the slope. M is the slope. So for example, if y equals minus 3x plus 6, the slope is negative 3. If y equals 1/2 x plus 9, the slope is 1/2. A slope can be a positive number or a negative number. It can be a whole number, an integer, or a fraction. It can be a decimal. Y equals 0.00314x minus 0.12. That's a straight line, and the slope is 0.00314. That's our symbolic. We've talked about that a bit before. Let's talk about graphical. Slope, as I said, is the change in y over the change in x. You could also think about that as how does y change when x changes by 1 unit? So these are equivalent, but sometimes it's easier to think about the change in y when x changes by 1 unit. And sometimes it's easier to think about the change in y divided by a change in x. So in this first graph, our axes are here and here. And the function or the equation of the line gives us this line right there. And as x changes by 1 unit, y goes down 2 units. X goes up by 1 unit, y goes down by 2 units. So the slope is negative 2. And notice no matter where I do this calculation, the slope is always going to be the same number. In this graph, here are my axes, and here is my line. In this case, it's harder to see what happens to y when x changes by 1 unit because that point right there is not on a grid line. It's not an integer. So instead, finding the slope, it's easiest to count from a coordinate point to a coordinate point that are both on the grid lines or are both integer coordinates. This point here is 3, 2. This point here is 6, 4. And so x goes up 3 and y goes up 2. The change in y divided by the change in x, 2 divided by 3, the slope of that line is 2/3. And that's how you pick out the slope of most lines when it's a graphical representation. I want to show you two other graphs where we might be thinking about slope. Now they're both lines, but they're special lines. So in this first one, there are my axes, and this line is horizontal, the line is flat. So if I were to calculate slope, when x goes up by 1, y has 0 change. Slope is change in y over change in x. So the slope, or sorry, the change in y is 0 when the change is x in 1. So the slope is 0. Horizontal lines have 0 slope because the output never changes. The change in the output is always 0, so the slope is 0. The rate of change is 0. compare that to a vertical line. So here are my axes, and here's the line that I drew, which is a vertical line. Slope is change in y. Well, no matter what change in y I pick, my change in x is always 0. A vertical line, the x value never changes. Any number divided by 0 is undefined. If you divide 2 by 0, that's undefined. 5 divided by 0, undefined. Negative a half divided by 0, undefined. So since the slope is a number divided by 0, the slope of a vertical line is always undefined. All right, that concludes our overview of slope using a graphical representation. Now let's use a numerical representation. Ignore this part at first, and let's just look right here at this table on the left. So I have a table that represents a linear equation or a linear function or a linear model. The x's are -2, -1, 0, and 1, and the y's are 3, 5, 7, and 9. So if I want to figure out the change in x, I say how much is x changing from -2 to -1? It's going up by 1. And it goes up by 1 each time, and y goes up by 2 each time. Slope is change in y over change in x. Right, there's my change in x, it's 1. And there's my change in y, it's 2. So the slope is 2 divided by 1, which we write as 2. A lot of tables, if we're lucky, will just increase x by 1 each time. But that's not always the case. Let me draw another one here. And then we'll get to the third example. Here's a table where the x changes by 2 each time. And I'll confirm that. And the changes in y are going to go down by 3 each time. But the slope is still the change in y, which is -3, divided by the change in x, which in this case is 2. So even when the change is not 1 each time in x, you can still do the division to find the slope. And in my last example, not only is the change in x not 1 each time, in fact, the change is not the same each time. And that could mean a couple things. It could mean this function is not a straight line. But we'll know if it's a straight line when we compare the change in y divided by the change in x. 5 to 9, x goes up by 4. 4 to 3, y goes down by 1, so the change is -1 over 4. 9 to 12 goes up by 2. 3 to 2.5 goes down by -0.5 or -0.5. So the change is -0.5 divided by 2. Well, that's also -1/4. So the rate of change is the same, even though the step size is different. And it's the same thing here. 11 to 13 goes up by 2. 2.5 to 3 goes down by 1/2. That's also -1/4. So the change in y over the change in x is always -1/4. And so that is the slope. All right, that was tables, how we often see numerical representation, but we can also see them just as ordered pairs or coordinate points. So an example you're going to see in your homework, and often when you change from a verbal to a numerical representation, you end up with coordinate points like this. We're going to find the slope of the line that connects -3, 9 to 4, 22. So our first coordinate point is x1, y1 equals -3, 9. And our second coordinate point is x2, y2 equals 4, 22. Now, we can do this purely with symbols, but I like to build a table because these coordinate points are entries in a table. So I'm just going to build a table so I can use the skills that I've been working on already here and here. So if I build a table, my first entry is x is -3 and y is 9. And my next entry is x is 4 and y is 22. And then I just look at how it changes. From -3 to 4, I have to go up by 7. That's my change in x. And from 9 to 22, I go up by 13. That's my change in y. And so the slope is the change in y divided by the change in x. The slope is 13/7. And I've used my numerical skills, my tables that I've been practicing to find the slope very easily. If we want to find it symbolically, remember that slope is change in y over change in x. The change in y is 22 minus 9. Another word for change could be difference. And you find a difference by subtracting. So the change in y is 22 minus 9. And the change in x is 4 minus -3, which is 4 plus 3, or 7. And again, we find that the slope is 13/7. So in addition to seeing slope is change in y over change in x, we often see it written as y2 minus y1 over x2 minus x1. Okay. So that's our numerical. And then we have our verbal. So there are a lot of questions that you can write that involve slope. In my earlier video, I didn't want to write them. I decided I actually am going to add a question to this video where we pull the slope out of a verbal representation. But what I want you to keep in mind is if you're looking for the slope, look for words like speed that involve speed, or that involve rate of change, or that have something that looks like every x, y happens. So for example, Joe drove 15 miles per hour. That's a speed, so 15 is the slope of our distance function. Anne was pouring out water at a rate of 3 milliliters per second. So the slope of that equation or function is 3 milliliters per second. Or every 2 days, that's our every x, every 2 days, 3 more lilies bloomed. Every x, y happens. Our slope is 3 lilies every 2 days, or 3 divided by 2, or 3/2 lilies per day. All right, sometimes you need to find the slope from a verbal expression, and you're not given a rate of change. So let's look at this example. So Ed has, let's see, I want to start over. On day 1, on day 5, let's say on day 5, Ed has 13 Pokemon cards. Ed gets the same number of additional cards each day. And on day 8, Ed has 31 cards. What is the slope of this linear model? Right? If he's adding the same day, if he's adding the same number of cards every day, that's a linear model. But you might actually, instead of seeing like that, you might say like, how many additional cards does Ed get every day? And this is how we would probably write slope. How many additional cards? What's the change in the cards does Ed get every day? How many what's the change in y for the change in x? So in order to answer this, we're going to convert it to from a verbal to a numerical representation by coming up with our 2 points, x1, y1. Well, that was on day 5, that had 13, and x2, y2 was on day 8, and had 31. And now we can build our table, or we can do it symbolically. But I'm going to do the table because this is really how I recommend you do it until you get super comfortable. 5, 13, that's one of our coordinate points, and 8, 31, that's one of our coordinate points. So to get from 5 to 8, we add 3 to x, and to get from 13 to 31, we add 18 to y. So our slope is 18 over 3, and this fraction reduces to 6 cards per day. There we go. That's how you can find the slope from a verbal representation. You change it into a different representation, and I find the easiest one to be the numerical representation. Okay. So one last page of notes to talk through. There are actually 3 ways to write linear equations. 2 of them that aren't in slope-intercept form. Here's our slope-intercept form. That's the one that I like to use because you can read off the slope and you can read off the y-intercept, and those are generally the 2 most valuable pieces of information. There is another form called point slope, and it looks like y minus y1 equals m times x minus x1. M is still the slope, so at least you can read the slope off. But you don't have a y-intercept. Instead, you have a specific point, x1, y1. A y-intercept itself is a specific point, so this is pretty similar. These are pretty similar, but it's written a little differently. Know that you can still find the slope from the formula. So here's an example of point slope form. Y minus 3 equals 2 times x minus 12. The slope is 2, and the coordinate point is 12, 3. If you see an x minus 12, it means the coordinate point is a positive 12. And if you see a y minus 3, it means the coordinate point is a positive 3. That's 2 of our forms. The third form is called standard form. This one tends to come out of verbal questions, very specific verbal questions, and we'll study those later. But right now, I just want you to show you what the form looks like. In general, it's a times x plus b times y equals c. A, b, and c are all numbers. X and y are the variables. So for example, 2x plus 5y equals 10. This is a linear equation, but it is in standard form. It is not in slope-intercept form. And when you see the standard form, it does not show you the slope. I cannot just read the slope off as one of these numbers. The slope is neither 2 nor 5 nor 10. It is something else. I cannot just see the change in y for a change in x. So in order to find the slope, which we usually want to do, we need to convert standard form. And I like to convert it to a visual representation. In Desmos, it's really easy to convert standard form to a visual graph. So I'm going to show you how to do that. Here we are with Desmos, and all you have to do with the standard form equation is just type it in, and there it is. There's our graph. Now I can use my graphical skills. I've got a couple points on here that are really easy to find. So change in y over change in x. Well, y goes down 2 when x goes up by 5. All right. This is not mathematical type, so Desmos doesn't like it, but I'm getting the notes on there. So if y goes down 2 when x goes up 5, the slope is minus 2 over 5. And it's as easy as that. Instead of messing with the algebra, which you know how to do because this is a literal equation and we can solve it for y, but you can also graph it and use your graphical representation, and that is very good mathematics. Now, if you don't happen to have Desmos or other ways to quickly represent it, visually. Or if you want to practice doing it symbolically, which I also recommend, you can find slope-intercept form by solving for y. This is solving that literal equation. I don't know if you're ever going to hear this term again after this class. I'd never heard it before this class, and I've never heard it in another one. But this can help get you back to the proper section. So I'm going to solve 2x plus 5y for y. So treat this as a whole term, subtract 2x from both sides, and then I get 5y minus 2x plus 5y equals negative 2x plus 10. Then divide both sides by 5, and I have y equals negative 2/5 x plus 2. And the slope is negative 2/5, just like my Desmos picture showed me. All right, that wraps up this video. Hopefully I got the correct screen captures this time, and I'll see you for our next video. Thank you.